Welcome to the Explainer, everyone. Today, we're stepping into what I like to think of as the ultimate command center. Have you ever wondered how we take the messy, chaotic reality of our physical world and somehow translate it into a structured, highly searchable, and visually stunning digital simulation? Well, that is exactly what we're going to explore today. We're going to walk through the exact blueprint used to construct a digital representation of our physical space, literally building it from the bare geometric wireframes all the way up to complex, lightning-fast databases. So, to do this, we really need to understand our ultimate goal here, creating a digital twin. A digital twin is exactly what it sounds like, a comprehensive, data-based model that describes our environment. It allows us to abstract the real world and store it in a structured way within a geographic information system, or GIS. You can kind of think of this explainer as the step-by-step boot-up sequence of our geospatial database. We aren't just making a pretty picture here. We are actually teaching a computer how to understand physical space. Okay, let's dive into this. Here is our system initialization checklist. We're going to build this layer by layer. 1. Geometry. 2. Thematic scales. 3. Conceptual models. 4. Topology and time. And finally, number 5. Geodatabases. Section 1. Geometry. Vectors versus rasters. Before we can track traffic or map out a forest, we've got to establish our foundational spatial architecture. And it essentially comes down to a grand debate: the vector model versus the field-based raster model. If you're trying to represent a sharp object, like, say, the exact outline of a building or the crisp center line of a highway, you definitely want the vector model. It relies on precise points, lines, and polygons. But if you're mapping something continuous that exists everywhere across a landscape, like temperature or terrain elevation, you need the raster model. Rasters divide the world into these continuous pixel grids where every single cell holds a specific value. And this brilliantly illustrates that difference. Notice the simple geometric elegance of the vector model: distinct points, clean line strings, and sharp polygons representing discrete objects. Contrast that with the raster model. That is a continuous value field where every row and column creates a cell. You see those numbers, 100, 50, 20? Those might represent elevation in meters. And when we apply a gray value coding to those numbers, boom, a visual map emerges instantly right from the grid. Now, for those vector geometries, we absolutely need strict rules, which brings us to the simple feature model. This is the gold standard for defining planar objects. It doesn't just dictate what a polygon is, it actually defines the methods for spatial queries. It lets us ask the system things like, hey, do these two shapes overlap? It standardizes everything in text formats like well-known text or binary formats like well-known binary, so different software systems can talk to each other seamlessly. But what if we want the precision of vectors combined with the continuous coverage of a raster? Enter the Triangulated Irregular Network, or TIN for short. This incredibly futuristic wireframe is generated by algorithms that select morphologically important elevation nodes and connect them with edges. This forms these non-overlapping triangles, called faces, weaving together a continuous 3D surface. Sure, it's computationally heavier to build than a simple raster grid, but it allows us to perfectly capture sharp terrain features like break lines and ridges. Section 2. Adding meaning. Thematic scales. So the crucial point is that a wireframe building is really just a wireframe until we give it attributes. Computers need to know exactly what kind of data they're looking at to map it correctly. We do this through thematic scales. Nominal data is purely qualitative, like land cover. A forest isn't greater than a city, right? They're just different categories, so we shouldn't use sequential colors for them. Ordinal data adds a sequence, like forest condition levels ranging from poor to excellent. And finally, cardinal data is quantitative. This is the hardcore metric data, like population density, where we can actually run real mathematical calculations. Section 3. Structuring data. Conceptual models. Okay, so with our geometric shapes and thematic meaning established, we have to impose strict conceptual rules. We need to maintain order and prevent our digital twin from just becoming a chaotic mess of unconnected facts. We utilize 3 main conceptual modeling frameworks for this. First, the layer model, which is wonderfully intuitive. It just separates information into thematic layers, so all the roads are on one layer and all the buildings are on another. Next is the entity relationship model, or ERM. This maps out real objects as entities and explicitly defines how they relate to one another.
Finally, the Unified Modeling Language, or UML, takes it a step further by adding operational methods to the entities, essentially giving our map the ability to answer functional queries. Now, what's really interesting about this is how these abstract concepts link together physically and logically. You start with the physical layer model, stacking buildings over roads. Then, the ERM diagram shows the explicit logical relationship. It explicitly tells the system that buildings are located with respect to roads. And then, the UML diagram formalizes this whole thing into programmatic classes, assigning string and integer attributes alongside the actual query methods that software will run to retrieve this data. It's a really beautiful translation from a visual map to pure logic.
Section 4. Connecting reality, topology, and time. Right now, our digital twin is essentially just a static throwing. To initiate the next phase, we need to teach it the actual rules of physics, spatial connections, and movement through time. So let me pose a question to you. How does a computer actually know two roads intersect? As humans, we look at a screen, we see two lines cross, and we instantly know, yep, that's an intersection. But a computer doesn't. To a machine, they are literally just two independent lines drawn in the same digital space that happen to share some coordinate pixels on your monitor.
If you just dump raw digitized lines into a system, you get what cartographers humorously call spaghetti data. It's just a pile of unstructured digital noodles. Because there's no topological connection there, a route-finding algorithm is going to completely fail. It'll hit tiny microscopic gaps between lines, called undershoots, or lines that cross over too far, called overshoots, and the GPS routing will just break.
So to fix this spaghetti data, we have to build a highly functional network layer using topology. This is a rigorous process. The system has to mathematically calculate the exact intersections of crossing lines and automatically eliminate those erroneous undershoots and overshoots. We also have to apply user-defined thresholds, basically telling the computer when a gap is just a drawing error versus when a gap is an actual dead-end street. And even with high-level automation, this topology building process almost always requires final visual checks by humans just to ensure those nodes and edges are perfectly secure. And spatial rules also mean we have to account for time. Our digital twin can handle time in two ways. First, there's static temporal modeling, where we take snapshots of changing properties across multiple fixed time points, like, say, mapping deforestation over a decade. But then we also have dynamic moving features. This is the real-time tracking of position data for moving objects, like live pedestrian movements or delivery trucks, which relies on constantly updating movement profiles.
Section 5. Storing it all. Geodatabases. All right, we've reached the final step of our boot sequence. Everything gets filed neatly into the system's core tabular architecture, the mighty relational data model, which powers modern geodatabases. This is a highly efficient setup where each row is a distinct record, like a single house, and each column is an attribute, like the owner's name. By normalizing the data into different tables and connecting them seamlessly via pointer IDs, we completely prevent data duplication and keep the whole system incredibly fast.
Let's see how this builds together and how elegantly those abstract entities transform into clean tables. The entity relationship model translates directly into the relational data model. Buildings get their own clean table and roads get their own table. Instead of typing main road into every single building record, the building table simply points to road ID 21. Through a database management system using structured query language, or SQL, our GIS can now read, analyze, and visualize this entire spatial reality instantly.
And there we have it. Our system is now fully initialized. We've gone from an abstract reality to a fully functional geospatial database. I want to leave you with this final thought. If you were constructing a digital twin of your own neighborhood right now, how would you model the data? What would your vectors be? What would your raster fields track? It completely changes the way you look at the physical world around you, doesn't it? Thanks for joining me on this explainer, and keep exploring.